Chapter 11, Universal Gravitation and Satellite Motion. This lecture will help you understand how gravitation acts between all objects with mass and explain the concept of a gravitational field. Legend has it that Newton saw an apple fall from a tree, and it occurred to him that the apple was attracted to the center of the earth. Newton reasoned that if the apple was attracted to the earth, why not the moon? Newton posited that gravity is a universal attractive force between all objects in the universe. Newton's laws of motion explain how objects interact with the world and with each other. Newton's first law, also known as the law of inertia. Originally formulated by Galileo, Newton restated it as an object at rest will remain at rest, and an object moving in a straight line at constant speed will not change its motion unless an external force acts on it. Newton's second law states that when a force is exerted on an object, its acceleration is inversely proportional to its mass and directly proportional to the applied force. Newton's third law states when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and in opposite direction to the first body. Known as the law of action and reaction, if object A exerts a force on object B, then object B exerts an equal but oppositely directed force on object A. This pair of forces is called an action-reaction pair and is present in every interaction between objects. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. On Earth's surface, the acceleration due to gravity is approximately constant and directed toward the center of Earth. Newton was able to explain that the gravitational pull of the Sun keeps the planets moving in their orbits. Without the Sun, the planets would move in a straight line through the universe according to the law of inertia. But the Sun exerts a constant pull on all planets. This force bends the path toward the Sun, pulling the planet into an elliptical orbit. Previous Aristotelian thinking assigned different causes to different types of motion. By unifying all motion, Newton shifted the scientific perspective to a search for large, unifying patterns in nature. Newton found that Kepler's laws are all a consequence of his laws of motion. The implication of Newton's law of gravity is that massive objects actually orbit about their common center of mass. If one object is much more massive than the other, the center of mass is not far from the center of the more massive object, like two people on the seesaw. For objects more equal in mass, the center of mass is between the two. The two images show the center of mass, called the barycenter, of the Earth and the Moon, and of the Sun and Jupiter. For the Earth and the Moon, the barycenter is 1,737 kilometers below the surface of the Earth. For the Sun and Jupiter, the barycenter is outside the Sun. The barycenter of the solar system is dominated by the Sun and Jupiter, but all the planets play a small part. The image shows the barycenter over a 50-year time span from 2000 to 2050. The faint yellow line is the outline of the Sun. Notice the barycenter moves in and out of the Sun as the planets all make their orbits about the Sun. A free-falling object is an object that is falling under the sole influence of gravity. No other force acts on the object. Any object that is being acted upon only by the force of gravity is said to be in the state of free fall. There are two important motion characteristics that are true of free-falling objects. Free-falling objects do not encounter air resistance. and all free-falling objects on Earth accelerate downwards at a rate of 9.8 meters per second squared. The Moon is in free fall around the Earth. It is its inertia that keeps the Moon orbiting the Earth. As the Moon orbits the Earth, the centripetal acceleration is balanced by the force of gravity. At the surface, the force of gravity can be written as m times little g, which is 9.8 meters per second squared. Newton, using the acceleration of gravity, calculated what the period of the Moon would be if it falls at 9.8 meters per second squared. He found it should be around 11 hours. This does not match the actual value of 27.3 days. Newton concluded that the acceleration of gravity at the Moon cannot be 9.8 meters per second squared. To find the acceleration of gravity at the Moon, he inverted the equation. Using the known period of 27.3 days, he found an acceleration of 0.00272 meters per second squared, a much more reasonable value, and one that showed that the force of gravity decreases with increasing distance. Newton's law of gravity states that for two massive objects of masses m1 and m2, the gravitational force is proportional to the product of their masses divided by the square of the distance between them. G is called the gravitational constant. The forces are directed along a straight line joining the two objects. The gravitational force is an inverse square force. Doubling the distance between objects means the gravitational force is 1/4 the original value. If you triple the distance, the gravitational force drops to 1/9 the original value. Since big G is so small, it means that the attractive force between two 1 kilogram masses whose centers are 1 meter apart is 6.7 times 10 to the minus 11 newtons. This is 100 billion times weaker than the force of gravity from the Earth on either of the masses. Although weak, gravity is a long-range force. Gravity keeps the Earth orbiting the Sun and the solar system orbiting the center of the Milky Way galaxy. The Cavendish experiment was performed in 1797 and 1798 by British scientist Henry Cavendish, and was the first experiment to measure the force of gravity between two masses in a laboratory. Two large balls were positioned on alternate sides of a horizontal wooden arm. Their mutual attraction to the small balls caused the arm to rotate, twisting the wire supporting the arm. The arm stopped rotating when it reached an angle where the twisting force of the wire balanced the combined gravitational force of attraction between the large and small lead spheres. By measuring the angle of the rod and knowing the twisting force, the torque, of the wire for a given angle, Cavendish was able to determine the force between the pair of masses and subsequently the gravitational constant. The force of planet Y on planet X is blank, the magnitude of the force of planet X on planet Y. A, 1/4, B, 1/2, C, the same as, D, twice, or E, 4 times. The answer is C, the same. This is by Newton's third law of equal and opposite forces. The gravitational force between two asteroids is 1 million newtons. What will be the force if the distance between the asteroids is doubled? Answer is A, 250,000 newtons. By the inverse square law, doubling the distance decreases the force by a factor of 1/4. Three stars are aligned in a row. The net force on the star of mass 2m is to the left, to the right, 0, not enough information to answer. Answer is A, to the left. The force of the 5-mass star on the 2-mass star is larger than the force of the 1-mass star, so the net force will be to the left.